Electric vehicles, EVs, are automobiles that run entirely on electricity. EVs are environmentally friendly because they do not use fossil fuels. Instead, they use lithium-ion batteries. According to Bloomberg, electric vehicles will become equally affordable with conventional cars as early as 2022 as the cost of batteries declines. Energy capacity for current commercialized lithium-ion battery in EVs is still not enough, where it only has a driving range of 400 km per charge, and the costs are still high due to higher cobalt content in lithium-ion battery. Till now, cathodes with nickel content of less than 60% are fully commercialized, and this is still not good enough for EVs industry, where they need a higher energy density. Objective of study. First, to determine the purity of synthesis using X-ray diffraction, XRD. 2. To determine the morphology and crystal dimension of synthesis cathode materials using field emission scanning electron microscope, FESM. Third, to determine the elemental composition of cathode materials using energy dispersive X-ray spectroscopy, EDS. Lithium-ion batteries are made up from anode, cathode, separator, electrolyte, and two current collectors, which is positive and negative. Lithium is stored in anode and cathode. Electricity is produced when electrons migrate from the anode to the cathode and vice versa. A charge is produced at the positive current collector by the movement of the lithium ions, which release free electrons in the anode. The anode releases lithium ions to the cathode as the battery discharge and produce an electric current, which causes a flow of electrons from one side to the other. The lithium ions are released by the cathode and received by the anode when the device is plugged in, which is the opposite of what discharging process occurs. To make LiNi0.9Co0.1O2, the mass of nickel, cobalt, and dope was weighed and dissolved separately in the ionized water at room temperature. After that, the mixture was stirred for around 30 minutes to obtain a homogeneous solution. Then, sodium hydroxide solution, an appropriate amount of ammonia solution as a chelating agent, was added to the mixture. After that, the precipitate was filtered and washed several times, then dried overnight. The precursor obtained was grounded using adit mortar to get fine powder. The precursor was extensively grounded after being combined with lithium carbonate or lithium hydroxide. The mixture was sintered at elevated temperature. The materials was characterized using XRD after they have undergone annealing process. Table shows the synthesis material with the chemical formula for each batch. I can conclude that batch 1, batch 2, and batch 3 do not reach purity, while batch 4, batch 5, and batch 6 are pure. Figure shows the XRD result for B1, B12, and B13. 3 of these samples using the same dope, which is niobium, but different lithium-ion battery for each sample. For B1 and B12, both NB dope mixed with lithium carbonate, while B13 mixed with lithium hydroxide as their lithium source. XRD patterns reveal that only B13 sample were isostructural to LiCO2 crystal structure with a reference, which is sample mixed with lithium hydroxide, and this structure has higher cation mixing. However, B1 and B12 do not reach purity as the reference pattern because this sample use lithium carbonate. Thus, it can be concluded that using lithium hydroxide as a lithium source is much effective to produce pure and single phase of layered structure. XRD patterns reveal that only B23 sample were 100% pure, that isostructural to LiCO2 crystal structure with ICDD database pattern. The 104 peak is shorter than 003, indicating that there is less cation mixing present in the crystal structure. Reference intensity ratio (RIR) measures between the 003 and 104 peaks were used to assess the presence of cation mixing. It is reported that if the RIR value is higher than 1.2, the crystal structure will have low cation mixing, which results in good cation ordering, which in turn results in good electrochemical property. Based on result, The RIR value for B13 is lower than 1.2, which indicates a higher cation mixing present in the crystal structure, implying pure stability. The RIR value for B23 is 1.9835, which is higher than 1.2, implying the material has the lower cation mixing and has the potential to show good electrochemical behavior. Only the NB-doped NCNB911 sample is put through morphological analysis using FISAM. For this sample, the FISAM pictures were captured at magnifications of 1000, 5000, and 20,000. Furthermore, the elemental composition of the material was determined using EDS on the B23 sample. The figure presents the study area image, the spectra, and the elemental data for the B23 sample. The findings indicate that the nickel content is nearly identical to the theoretical predictors, which is 90%. Cobalt and zirconium content, which should make up 10% of the total atomic percent, respectively, are greater than supposed to. Last but not least, the mapping analysis was carried out on the B23 sample to determine the distribution of elements inside the sample, and the spectra are displayed in the figure. The mapping analysis reveals that the elements are evenly dispersed. For recommendation, divide into two. First, battery testing. It is used to see performance, capacity, and retention. Another one is to play with another dope to get purity.